Hey everybody, and welcome back to another video. So the biweekly contest number 54 happened this morning, and it's the afternoon now, and I'm getting around to recording the solutions. So I actually joined this contest like 10 minutes late, so that didn't really help my cause. I was only able to solve the first 3 problems, and I think I ended up getting like, yeah, not even in the top 1000 SMH. Okay, whatever. Yeah, so my approach for the final problem was correct, but it was just a nightmare to implement it. Um, but in this video, I'll just be going over the problems that I did manage to solve 1 through 3, and if I'm feeling up to it, I'll figure out this. I'll finally get around to implementing this 4th one and make a video on that. So yeah, this video will go over problems 1 through 3 in biweekly contest number 54. So the first problem, check if all the integers in a range are covered, is fairly simple because of the small constraints. So in this problem, you are given a 2D array. You're given an array of arrays, basically, and every array inside this array represents a range that is covered. So it's like inclusive of both the endpoints, right? So this array here means that the interval from 1 to 2 is covered. This one here means 3 to 4 is covered, etc. And then you're given 2 numbers, which are the endpoints that you need to check. And you need to check if every integer within the range you're given here is covered. And so in this test case, it's fairly simple. We can see that 2 is covered by in this interval, 3 and 4 are covered by this, 5 and 6 are covered, and 5 is covered in this interval. So 2 through 5 is covered, and in this one, it's not. And so because of the small constraints, we can just do this exactly like kind of brute force. We can just maintain an array because at most the index of the start and end of a range that we need to check is 1 in 50. So we can just make an array that's 51 things long. So because the end can be equal to 50, so we need 50 to be a accessible index in the array. Then for every range that we are given, we can just fill that in inside of our array. So we go from start and less than or equal to end because yeah, the interval is inclusive, so you want to go all the way to end. Then we set that to true. So all the values in our Boolean array, which are covered by the intervals, will be set to true. So it'll look something like this. So if we have a Boolean array of a bunch of things, all the values which are covered will be true, and all the ones which aren't will be false. And so that way, when we are given this left and right, we can just start from left, go to right, and check if our array here is false. Because if it's false, then we know that this entire interval here isn't all covered, but otherwise we return true. So like for example, if this is our interval, we can see that all the values are covered, so we can we'll never enter into this case and we'll return true. But otherwise, if there is like a false in there, we know that not all of the values are covered. So yeah, that's question 1. Pretty simple. Yeah, you just do exactly like how you think. And yeah, so let's move on to question number 2. So in this question, you're supposed to find the student that will replace the chalk. And so what will happen is that you have k pieces of chalk. So you're given an integer k, and every array inside of chalk, like every integer inside of this, means that student will use that many pieces of chalk. So the student number 0 here will use 5 chalk, this guy will use 1, and this guy will use 5. And since there are 22 pieces of chalk, after one cycle, there will be 11 pieces of chalk left. And then in the second cycle, the student number 2 will use up all the chalk, so k equals 0. But the person that makes k go negative, so like when there's not enough chalk for the student, that student will be the one that has to replace the chalk. So you're supposed to return the index of the student that will replace the chalk. So essentially, you're going to return 0, which means that student number 0 will be the first one that does not have enough chalk for him to use. And if we look at the constraints here, n is between 1 and 10 to the 5. So we know we have to be a little more clever about how we approach this, because at first glance, we can maybe just think about brute forcing this, right? We just loop through this array, subtract it from k, and then loop through it again, and then etc. But that we soon realize that doesn't work, because k can be up to 10 to the 9. And so let's just say our chalk array is filled with 1s. That's going to take forever. Let's be honest, because we'll have to loop so many times, and that will get a time limit exceeded for sure. So what we can actually do is we can realize that if like only the last cycle matters. So let's just say there are 25 pieces of chalk. Let's just say there are 25 pieces of chalk, and every cycle, let's just say our array looks like 1, 2, 3. Every cycle, 6 pieces of chalk will be used, right? Because each student, this one will use 1, this one will use 2, this one will use 3. Sum them up, that's 6. So we know that we could subtract 6 from 25 over and over until we get to the cycle where one student will run out of chalk. But we could easily skip a bunch of cycles. Instead of having to loop through this, we can just figure out that, well, 25, well, if you multiply 6 by 4, that means after 4 cycles, there will be 1 piece of chalk left. And since each cycle takes up 6 pieces of chalk, we know that somewhere in the 5th cycle, a student will run out of chalk. So if we can find this part instantly, then what we can do is we can just subtract that. Now we know I have 1 piece of chalk, and we can just loop through the array once to figure out which student will run out of chalk. And since we know this student uses 1 chalk and this student uses 2, this student will have enough chalk, because 1 minus 1, that's 0, that he'll still have enough. But when there's 0 piece of chalk and this student wants to use 2, well, obviously there's not enough, so index number 1 will have to replace the chalk. So now, and it's pretty easy to see that this sort of linear scan will be really fast. So now the problem is essentially, how do we find this number, this 4? How many cycles do we have to skip? So what we can do is actually binary search for it, because if we just start this number off at 1 and increment it by 1 until we find a number, that actually would be a little too slow, because sometimes we'll have to increment it a lot of times. Like for example, the case when k is equal to 10 to the 9 and all the numbers in our chalk array equal 1. That's just going to be disastrous, because we need to increment this 10 to the 9 times. But what we can do is we can actually binary search. We can have a left value of 0. Well, it doesn't really matter. We could also set it to 1. It just has to be like the minimum number. I think I set it as 0, but you can set it as 1. Yeah, set it as 0. It doesn't matter. We just need it to be like 0 or 1. And right will be the maximum this number can be. And since the smallest sum of this can be 1, let's just say there's 1 student and he uses 1 piece of chalk. By looking at the constraints here, this least can be 1, and there can be there's at least 1 element in the array. So this is the worst case. So at most, let's just say the starting number k equals 10 to the 9. So 10 to the 9 minus 1 times this maximum value. This maximum value will be 10 to the 9 as well. So we know at most there will need to be 10 to the 9 cycles. So we can have left this and right this, and then we can just check the middle and set this number to be the middle between the two. So the average of left and right. So then, because you set it to the average here, you can just check if this one will be the cycle that makes it so there's no more chalk left. And yeah, so if this number is too large and causes this to be negative, you know you want to set your right endpoint to the middle minus 1. And if this number is too small and you need more cycles, you want to set left equal to mid plus 1. And that'll narrow in on which cycle causes on like how many cycles you need to skip, right? Because you're wanting to skip this many cycles. So and at the end we'll want to use the right endpoint because we want to skip to the cycle that just before the one that caused it to run out. So because whenever we find a number that's too large, we'll make right one less than that. So right will end up being like the number that is like this number that we want right here. So this 4, it'll be the one that the number of cycles that cause the chalk to be 1 cycle before running out. And after that, it's fairly simple. So if you look at this, yeah, so you can I just computed a prefix sum here, but you don't need to do that. This just makes it easy because we can just look directly at this array here to find how many chalks are used every cycle, because since we're summing it all up, the last value will be 6. So we know that when it's this student's turn, they'll 6 pieces of chalk will have to be used. So yeah, this just computes the prefix sum here. So it'll look something like this: 1, 3, 6, and yeah. So here we perform the binary search. It's fairly standard, and yeah. So here we check the midpoint and we multiply it by, this is how many chalks are used every cycle, because that's the last number here. And we know that if this is exactly how like it divides into it an even number of times, then we will obviously return the first student, because after every cycle, let's just say there's like 12 chalks and every cycle uses 6. After 2 cycles, there'll be nothing, and then it'll be the first student up again. So we can just return 0. And otherwise, we set the left midpoint to that add 1 and right to that minus 1 to narrow in on this value just before the cycle runs out. And then we'll just use the right endpoint. We can subtract however many that is from k. So that's doing this 25 minus 6 times 4, essentially. And so now we know that there's this many chalks, and we can just go through our prefix sum here to find the first number that's greater than how many we have left. And that's the index of the student that will have to replace the chalk. Because if we imagine after this loop here, we'll have, let's just say, for example, we run into this, we have our prefix sum of 1, 3, and 6 here. Let's just say we have 5 chalks left. We know that after this student goes, there'll be 1 chalk used in total. After this student goes, there'll be 3 chalks used in total, and after this student goes, there'll be 6 used in total. So we know that when this student goes, since 5 minus 6 is negative, we know this student will have to replace the chalk. So yeah, because this number will represent how many total chalks will have to be used so far in the current cycle. So then you can return that, and you can just have this is pretty much a pointless return statement, but you need to do it so it doesn't throw an error. And so, yeah, this problem is fairly straightforward, but the only realization you have to do, which is pretty easy if you look at the constraints, is to just realize that you need to binary search for this number here to essentially skip to the cycle that a student will have to replace the chalk, because there will be a bunch of cycles where all the students use chalk, and there will still be chalk left. So you have to keep on cycling. So it's just important to skip all those cycles and go right to the cycle that'll cause a student to run out of chalk. So yeah, so let's talk about the third problem. And so this problem, yeah, this problem is mainly I would classify it as like a more of an implementation like problem, because actually thinking of the solution is pretty easy, but yeah, you just have to implement it in like a smart way. So yeah, so in this problem you're given like a matrix essentially, and it can be like a rectangle, whatever, and you're supposed to find the largest magic square within the grid. And so a magic square is when in this square all the rows, columns, and diagonals, like both diagonals, sum to the same number. So in their test case here, if you want to work it out, all these with the red highlighted box, every row, column, and diagonal will sum to 12. And this box, it doesn't have to be an odd number, it can also be an even number, it doesn't really matter. So what we can do here is, well, first of all, it's important to realize that yeah, this grid here, because M and N are the grid lengths, it will be at most a 50 by 50. So you can pretty much just brute force your way to solving this. So what you can do is you can, so let's just say we have a grid here, and it looks something like this, right? What you can do is you can just go through every like location in the grid. So here, 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 just loop through those, and treat it like the top right corner of a magic square. So we know that the 1 by 1 will obviously be a magic square, so we don't need to check that. Since it says here, every 1 by 1 grid is trivially a magic square, so we don't need to check that. And so what we can do is we can pretend like this is the top right corner of a magic square. And while you can make the square bigger, we want to check if that square is a magic square. So if we treat this as a top right corner, we'll want to check this if it's a magic square, then this, then expanding one more down, then this, and we can't expand more down here. So those are the three we need to check. And similarly, we can start from here at the top right corner. We'll check this one, then this one, then this one. And for every point, we can just check if expanding it causes it to remain a magic square, right? So just one more example, like if we treat this, we can only expand once like this. There's nothing more here to expand to. And yeah, so that's the first part. So for this loops through all the starting points inside of the grid, and this radius here essentially means how many squares you want to expand down by. So since we know this 1 by 1 is already 1, we don't need to check it. So we start radius off by 1. That just means we want to add 1 to this side and add 1 to this side. So our square will be this. Then we'll increment radius to count 2, so it'll check this square. And we do that until we can't expand it anymore. So this checks if you can expand it, and this as well, because I and j are the starting points. So let's just say this here is represented by I, j. So when you add a radius to it, since it's the top right corner, you want to make sure that you don't go out of bounds here by adding too much to I, which is the row. and you don't want to make sure you go out into here. So this just makes sure that you can expand the box. So while this box is valid, so if this 2 by 2 is valid, then we want to check if it's a magic square. But we just do that when this might be our current largest square so far, because we want to return the largest magic square. So if this has a chance to be the biggest magic square, then we want to check if it's a magic square, and if both of those are true, we'll just remember that this is our biggest magic square, and at the end we'll return the radius plus 1, because this is a 2 by 2 magic square, and well, no, this will be a 2 by 2 magic square, like right here, and our radius would have been 1 because we only expanded 1 down and 1 to the side. So we want to add 1, and let's say our radius is 2, we expand 1, 2 down and 1, 2 to the side, and check this square from our starting top right corner. We'll save a radius of 2, but the answer is 3, so we just add 1 to it. And that's the first part. So this logic essentially will just try every magic square inside the grid that can be tried. So by treating every one as a top right corner and expanding the magic square as much as it can, and seeing if that results in the largest magic square. So the second part of this solution is to essentially figure out how to implement the isMagic square, where you're going to be given the grid, the starting row and column, and the radius. This is the radius. So first we need to figure out what all the rows need to sum to. So for here, I can just start I at the row, and while it's less than or equal to the row plus the radius. So if this is if row is 0, radius is 1, we want it to go from 0, we want I to go from 0 to 1. So while it's less than or equal to adding the radius to it, we increment I, and we'll add that to our total. So now we know that we want all the rows, columns, and diagonals to equal total, because this is the total of one of the columns. So now we'll check all the rows. So we'll increment I through here once again. So I will go through all the rows. So it'll go like this, check the rows. And for every row, we want to just move in the column direction. So we start J at the column, and while it's less than that plus R, we increment it. So if this is our starting location, I will go from here, here, and for everything that we go to, J will go like that, and yeah, so we'll be able to sum up all the rows. So we have a row, and we sum it all up, and if it's not equal to the total, we will return false, obviously. And if it's true, then we can move on to checking the columns. So we'll use the same logic, but instead J will go from the columns first, and for every column we'll check this row. So we'll find the sum of these columns, and earlier we were finding the sum of these rows. So then we can just check the diagonals using this loop. So we can just have two variables here, and so we can just start going from 0 to the radius, and since we know our starting point here is the starting point, we know that we can just add add I to the row in the column to get the diagonal. So let's just say we start here. Let's just say this coordinate is like 1, 1. This one will be 2, 2, 3, 3, etc. So all the way until radius, right? Because this will be R equals 2, R equals 1, and we can just add R to both of these starting locations. So this diagonal does exactly that. It'll sum up everything in this diagonal here, just by adding this number that we increment, starting from our starting location. So it'll increment 1, 2, like that. since we're adding it to both row and column. And this just sums the other diagonal, like that. Looks like this one. We know that the row will go from here to here. There are multiple possible ways of doing this, but in this one, the column will just start off at the column plus radius, and it'll just go 1 in this direction every time. So we can just do column plus radius and subtract this number that we're incrementing, and this will sum this diagonal right here. And yeah, so after summing these two diagonals, we can just check if they're equal to total, and if one of them is not, we return false. Otherwise, it passes all the tests to be a magic square, so we can return true, since we know all the rows, columns, and diagonals sum to the same amount, which is total. So yeah, so once you figure out these two parts, the testing if it's a magic square and trying every magic square inside of this grid by treating each location as a top left corner for a magic square, then you can just save the largest radius you end up finding and return that plus 1. So if we submit this, it gets accepted. And yeah, so this is more of a can you implement this, since with the small constraints, it's the straightforward solution is going to be the one that's going to work, because yeah, there's not going to be like any fancy trick you can use to find a magic square quicker than just trying all of them and seeing which one is the largest. So yeah, that's about it for this video for the first 3 problems. Thank you very much for watching, and I'll see you later.